All right. So last time in statistics, what am I saying? God, it's been a long day already. So last time in college algebra, we were looking at synthetic algebra. Jesus, still doing synthetic division. Today we're going to put synthetic division to the task. 3.3 is on finding zeros of polynomials. The first one we actually saw already. This was from last section. If f of x can be written as x minus k times q of x, then x equals k is a root, or a solution to f of x equals 0. Which plays along with the other thing we learned last time, which was the remainder theorem. F of x can be written as x minus k times q of x plus r. If f of k equals 0, then r is 0. And k equals a factor. And x minus k is a factor of x of x, of f of x. We did all that stuff last time. Those are just tools that we're going to use going forward from here. But if you want to do a quick problem with it, is, let's see, x equals -4, a solution to f of x equals 3x to the 4th minus 48x squared plus 8x plus 32. Now, sometimes I think doing the remainder theorem is easier. But not in this case. I got to pull out a calculator because I don't work with -4 to the 4th power very easily. And -4 cubed, and like there's some big numbers going on here. And I think they might get easier with synthetic division. So let's check it out. Unit 3, and I multiply it, and I get -12. If I add -12 to -48, I get -60. And I can see pretty quickly that this is going nowhere. What did I do wrong here? I missed a 0. Let's try that again. I missed 0x cubed. So x minus 4 is a solution. not x minus 4, x equals -4 is the solution. And if we want to see what it looks like as a factor, just solve this for, make the right side equal 0. Let's add 4 to both sides. And get x plus 4 equals 0. And so x plus 4 is a factor. So let's do the next one. We'll start with a cubic and we'll find all the solutions. All the roots. We'll factor a cubic completely. As long as we know one of them. Does anyone need it up longer?
Actually, I have.
So let's start with f of x. Equals 6x cubed minus 37x squared plus 32x plus 15. And I can tell you that x equals 5 is a 0. I want you to factor f of x. We'll do that together. We'll give you a chance to write that down. So, synthetic division will show me the remainder. And the coefficients of the smaller function. I know this at least turns into x minus 5 times q of x. We'll start there. I'm going to work with 5. Bring down the 6. 6 times 5 is 30. We add them up, we get -7. -7 times 5 is -35. 32 minus 35 is -3. And 5 times -3 is -15, which adds it to 0. That is easier to do and didn't require me to have a calculator than trying to plug in x equals 5. It would take me a while to do that in my head or, writing it out. I think synthetic division is pretty easy for the most part. Sometimes the numbers get unreasonable, and that usually tells you that there's no root. So this tells me f of x can be written as x minus 5 times these will be the coefficients to a polynomial of 1 degree smaller. We had x cubed. These are the coefficients to something that starts with an x squared. At this point, we have a quadratic function left to factor, right? We can factor this. So if I want to factor this, I need things that multiply to -18 and add to -7. -9 and 2 work. So I'm not going to forget my x minus 5. I've got 6x squared minus 3. I got minus 9x plus 2x. Factor it a little bit more. Here I can pull out a 3x. And I have 2x minus 3 left. Which means I need another 2x minus 3, and that means I got to do a plus 1. So finally, we end up with x minus 5 times 2x minus 3 times 3x plus 1. That's my f of x. And if I set this equal to 0, I find the solutions or roots. The roots are when x minus 5 equals 0, 2x minus 3 equals 0, and 3x plus 1 equals 0. For x equals 5, x equals 3 halves, and x equals negative 1/3. You guys ready for more? Anybody need this up longer? Huzzah. All right, so the rational zeros theorem. Let's say f of x equals a sub n x to the n plus dot 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 a sub 1 x plus a sub 0. Has rational roots, which are fractions or integers. An integer is just a fraction with a denominator of 1. Then they will come in the form of p over q, where p is a factor of a sub 0 and q is a factor of a sub n. So let's take a look at an example. Let's consider f of x equals 8x to the 4th minus 26x cubed minus 27x squared plus 11x plus 4. My a sub 0 equals 4. And factors of 4 equal plus or minus 1, plus or minus 2, and plus or minus 4. My a sub n is 8, the number in front. So factors of this are plus or minus 1, plus or minus 2, plus or minus 4, and plus or minus 8. So what are my options for P over Q? Well, I can always do it over 1, right? Because A sub n has a 1 in it. So I can always make my bottom 1, which means my top can be any of the values for A sub 0. It could be plus or minus 1, plus or minus 2, plus or minus 4. Then divide each of those options by the other numbers in the other factors of the A sub n. If I divide this by 2, I've got plus or minus 1/2. If I divide the 2 by 2, I get 1, but I've already got 1 on the list. So 2 over 2 gives me the 1, I already got that. 4 over 2 gives me a 2, and I already got that. So I don't want that one. Then I go over 4. I'll put each of these over 4. 1 over 4 is plus or minus 1/4. If I try dividing the 2 by the 4, I get 1/2. But I already have the 1/2 here. And if I try dividing the 2 by the 8, I get 1/4, which I already have listed here, so I don't need to write it again. Finally, I'll divide each of these by 8. And I get plus or minus 1 over 8. If I divide the 2 over the 8, I get 1/4, which I already have. And if I divide the 4 over the 8, I get 1/2, which I already have there too. So these are the only possible roots that are real numbers. We could have complex roots. If you wanted to write them in numerical order, you could. I think it can be helpful, but it can be a challenge. -4 is the lowest number, then -2, then -1. And then as I get closer to 0, the denominators get bigger for fractions. Zero is not an option. Because my constant isn't 0. This gives me a lot of things to check for synthetic division or the remainder theorem, right? That's a lot of shit to check. So let's take advantage of one other theorem for now. We'll add one other theorem. And we'll slowly add more as we go through the lecture. So Descartes' theorem. Rule of signs. Look at f of x. However many sign changes it has. Reveals how many positive roots it can have. Max positive roots it can have. So we had f of x equals 8x to the 4th minus 26x cubed minus 27x squared plus 11x plus 4. As I go from left to right, 8 is positive, this is negative, negative, positive, positive. We're just looking at the signs. This changes from positive to negative once, and then negative to positive once. So we have at most 2 positive roots. And you don't have to do anything but just look at the equation and count the sign changes. There is no math there. I didn't do a goddamn thing but just identify positive to negative or negative to positive. So if I get 2 positive roots, I don't have to check anymore. The other option for Descartes' rule of signs is looking at negative f of x, or f of negative x. Do the same thing. This reveals max negative real roots. So if I stick in negative x, I'm going to write what I'm doing first, and then we'll jump to what it means. So I plug each of those bad boys in. All the even exponents stay the same sign. This is just 8x to the 4th. This is 27x squared. And I got the 4. All the negative exponents, or the odd exponents, change signs. I've got a negative there, so negative cubed is another negative. So that makes this positive. And 11 times negative x is now 11x. Negative 11x. If I look at the signs here, positive, 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 negative, positive. And so we could have 2 negative roots. Sometimes it's a lot different. Sometimes there's like 1 negative and a lot more positive, and you're like, okay, this gets easier if I just get rid of the negative, or just get rid of the positive. So I have at most 2 real positive roots and 2 real negative roots that are rational. This does not reveal like shit like pi or square root of 2 as a root or things like that. This only reveals fractions as answers, so we may not find them all on the list. But we can go through and start checking some of them. Some of the easy ones to check are, let's put the function back. Let me rewrite the equation on a fresh blank page and write down our roots again. Or our possible roots. And possible roots were plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 1/2, plus or minus 1/4, and plus or minus 1/8. Now, I don't know about you, but I don't want to do this shit with fractions if I don't have to. So I'm going to check other shit first. I think the easiest ones to check are f of 1 and f of -1. I can do f of 1 pretty quickly. If I just stick in 1, this is 8 minus 26 minus 27 plus 11 plus 4 using the remainder theorem. Does this add up to 0? I've got 8 plus 11 is 19 plus 4 is 23 minus 26 minus 27. I can see that's not going to give me a 0. My positive number is 23 and it's smaller than both negative numbers. So I don't need to get a calculator for this. Then I'll try -1. All of the even exponents stay the same. And all the odd exponents, when I stick a -1, change sign. Well, this one might actually do it. So 26 minus 27 is -1. If I do 8 minus 1, I've got 7. 7 plus 4 is 11, minus 11. I'm going to get a 0 here. So f of -1 is a valid answer. And this is where I'm going to do synthetic division to find out a smaller equation. Sometimes it's helpful just to do the synthetic division from the beginning. So this is f of x equals, if I solve this, I get x plus 1 equals 0. And write this as x plus 1 times 8x cubed minus 34x squared plus 7x plus 4. My p's and my q's are still the same. They're going to be the same all the way down to the end. So what else could we try? We could try 2. We stick in 2 right here. I don't know, what am I going to get? 8 times 2 cubed minus 34 times 4 plus 7 times 2 is 14 plus 4. This is 32 times 3 is 8. This is 64. This is a big number. That's 132. That's not going to get me a 0. This can start being a pain in the ass. You got to check them all. So, what other rules do we have available to us? Let's take a look at, let's see, maybe I should just give you the rest of the reads for here. So we can finish this problem up. I have one of the negative roots already, so I know there's only one left. Maybe I should focus on negative roots. So maybe I shouldn't have tried a 2. Maybe I should try -2 and -4. So what is -2? If I stick it in, this is -64 plus 132 minus 14 plus 4. That's not a 0 either. F of -4 is going to be even worse. Sometimes -4 is -28 plus 4. Throw that in a calculator real quick. Calculator. -4 cubed is -64. I know that. So 8 times -64. Oh God. So this is negative. This is negative, and this is negative, and I only got +4. That's definitely not going to give me a 0. So if I have another negative root, and I have to, because they come in even numbers with the conjugate theorem, it's going to have to be -1/2 or -1/4. So let's try them. I think this is going to be easier to check with division, and I can use the smaller polynomial here to check it. When half of 38 is 19. And it's -13, so that's not a 0 either. Which means it's got to be -1/4. So we'll do an f of -1/4. -1/4 of 8 is -2. -1/4 of -9 is, or -36 is 9. 7 and 9 is 16, and -1/4 of 16 is -4. We see that it does add up to 0. So I can now write f of x equals x plus 1 times x plus 1/4 times 8x squared minus 36x plus 16. At this point, you stop doing P over Q. Just use quadratic formula, or when you're down to x squared, use quadratic factoring methods. I can pull a 4 out, make this a little bit easier. And I'm looking for things that multiply to 8. 2 times 4 is 8. But add up to -9. -1 and -8. And that part factors into x minus 4, 2x minus 1. And I still have the x plus 1/4. I still have the x plus 1, and I still have a 4. I probably wouldn't leave the 4 like that. I would probably move the 4 in here to get rid of that fraction right there. I would leave this in final form as x plus 1, 4x plus 1. When I multiply the 4 through, I got to distribute to both. X minus 4 and 2x minus 1. So this can be a pain in the ass. There are things that we can use to help speed it up. Let's talk about the intermediate value theorem and the bounded value theorem. Or the boundedness theorem, I think it's called. Does anyone need that up longer? All right. So the intermediate value theorem. First off, f of x has to have only real coefficients. That's the requirement. Then, if f of A and f of B have opposite signs, there's a 0 between them. The idea is something like this, where that stems from. Let's say that's my x and my y, and I've got A and B like this. They could be anywhere, I'm just putting them like here. If f of A is down here and f of B is up here, somewhere it's got to cross this x-axis. It may be there, it may be over here, it's got to cross somewhere. It has to cross the x-axis somewhere. So we can do that, use that to speed us up. Some other things that help. The boundedness theorem. All right, so we want f of x to be degree n greater than 1 or equal to 1. It can't be a constant. It needs to at least be a line or parabola or something larger. And that's requirement 1. Requirement 2, a sub n, or the leading coefficient, is positive. There's 2 scenarios here that have use. If we divide by, and both of these require dividing by x minus c. Or do synthetic division where x equals c. So option A, if the bottom row from synthetic division is all positive, or non-zero, I should say, or non-negative. Which means greater than or equal to 0. Then there is no root greater than c. So like if you find like x equals 1 as a root, but you've got 2, 4, 8, and 16 that are higher than it, and x equals 1 gives you a bottom row that are all positive, you can immediately cross off all the larger positive numbers. So we'll take advantage of this stuff as we're working through it. That requires c to be greater than 0. That's a requirement, sorry. That's an important fact that I omitted. If it's negative, we do introduce a way to change signs. Then if c is less than 0, and the bottom row alternates, there is no root less than c. I should say alternate sign. I didn't actually finish that thought. It's got to go plus, minus, plus, minus, plus, minus, or negative, plus, negative, plus, negative, plus. If there's a 0, it can be positive or negative, whichever, if it fits the rule. Those are a couple theorems that we will use. So let's take a look at this example next. What the hell? I'm just over here setting it down. Let's take a look at this example. So let's check for the positive roots by doing the sign count. So we'll do the rule of signs thing here. It goes from negative to positive, which is 1, positive to negative, which is 2, negative to positive, which is 3, positive to negative, which is 4. There can be 4 positive roots max. If I do f of negative x, all the odd exponents just change signs. This has no sign changes. So 0 negative roots. That's good. We just completely eliminated half the options that we could have. That's phenomenal. So let's figure out what we got. What's my P and what's my Q? So if I do my A sub 0, that's my -1. The only root of the only P I have here is 1. And A sub n is -2. I'm actually going to put negative plus or minus 1. Because those are possible values, but the Descartes says no. So Descartes says no negatives. Which means I can have plus or I can have possible positive roots. Are my P over Q equals 1 or 2 or 1/2. Only possible rational roots. Well, that's funny. This says I counted them, there's 2 here. It says there's 4 positive possible. Let's go through and find out what happens if we do it. Is f of 1 a root? F of 1 is the easiest one to check because I just drop all the x's in my starting thing and add them up. -2 plus 3 is 1. 1 minus 5 is -4. -4 plus 0 is 0. 0 minus 1 is -1. F of 1 is not one of the roots. F of 1/2. (1/2) times -2 is -1. It's -4. Wait, I'm not writing down the right signs here. There we go. 3 minus 1 is +2. Gotta write down the right signs, don't I? It really just changes shit if I don't. 1/2 of 2 is 1. I got -4. 1/2 of -4 is -2. And I get 2. 1/2 of 2 is 1, and I get 0. So x equals 1/2 is a root. It says I can have up to 4. It's the only root I have left that's positive. Let's check it again. Let's make a new box. Just extend this right here. Bring this down and we'll do 1/2 again. Let's see if it shows up again. (1/2) of -2 is -1. 2 minus 1 is 1. Oh, this is not looking good. 1/2 of 1 is 1/2. This is -3 and 1/2. This is for -7/2, which means this is -7/4, and that does not add up to 0. So that one is not going to have any more positive roots. Did I write this down right? (1 over 1 and 1 over 2). Those are the only positive roots. We check f of 1. Did I do that correctly? (2 plus 3 minus 5 plus 4 (7 plus), yeah. Huh. So the best we can break this down to is x minus 1/2 times this thing with coefficients right here. There's 4 other possible roots. Or 3 other possible roots? Why can't I come up with them? Any ideas? There's a reason. This only shows roots that are fractions or integers. So whatever these positive roots are, they're not fractions. They're going to be irrational numbers. Might be like square root of something or something like that. So there's up to 3 more positive roots. With a guarantee of at least 1. They're not rational though. The reason why I say a guarantee of 1 is that the Cartez rule of signs here on this problem said 4 possible positive roots. If there are any complex roots in this problem, or solutions to this problem, they show up in pairs. K equals A plus BI, and K equals A minus BI. So. This is two roots at a time. Can show up as complex. Which changes this to, I can have 4 positive roots, 2 positive roots, or 0 positive roots. If there's complex ones, they go away in pairs, which means it lowers the degree of the equation by 2. Now, notice on this one, we had f of x equals negative 2x to the 4th plus 3x cubed minus 5x squared plus 4x minus 1. We showed 4 positive possible roots and 0 negative possible. I knew once I got the 4 that I was going to have a 0 here for one good reason. A polynomial of degree n has at most n real solutions. So, how do we check it? If you've got f of x equals a sub n, x to the n, whatever the first exponent is, shows the maximum number of answers. Which is kind of neat. We'll go on to next. Let's take a look at that, at the following problem. How many positive roots can I have here? We just count the sign changes. Changes signs once, twice. 2. How many possible, how many negative roots possible? For that, we have to stick in negative x. And this changes the sign of all of your odd exponents. I've got 2 here. I'm going to tell you right away, this has 2 complex roots. One of the roots is x equals 2 plus I. So let's go through and figure out what roots we have. So x equals 2 plus I is a root. We are guaranteed that x equals negative or 2 minus I is a root also. So let's do synthetic division and figure out, let's reduce this as much as we can. It's not going to be the prettiest. Or we can try something else. Do you guys want to do that first, or do you guys want to try to find the other roots? If we do this, we're gonna do this twice. This is gonna knock this down to x squared, and we can do a quadratic formula, something like that. This is a possible route. Another possible route is just trying some numbers, seeing what we get, and if we find one of them, we know we can figure out if there's positive. We can reduce this by some. What do you guys want to do?
Seems like this one is like less guessing, just more work.
There's less guessing. It is more work though. Is that what you want to do? All right. So I will write down the coefficients. We had -1 to 2 plus I. We've got 1 plus I. This is where it gets a little tedious. That's a -1 though, so I got 1 plus 3i. I add that together, I got -16 plus 3i. Oh, this is getting ugly. Got -32 minus 16i plus 6i plus 3i squared. That becomes a -3. -35 minus 10i. Add those up, I've got 20 minus 10i. And I don't even need to do the last one. I already told you this is a root. I know this is going to be a 0. So I know this has to be -50 when I'm done, because I know it's a root. Which means I can use this one to do to the 2 minus I. I could use the
So
original one.
So you're saying that 2 plus I times 20 minus 2y is negative 50?
Yep. It's gotta be.
Is it?
Did I write down the problem right?
40. I mean, because I got positive 50.
That's supposed to be a negative 50 here. Sorry, you're right. There we go. My bad. That changes my answers up top here, doesn't it? 1 change, 2 change, 3 changes. And here's only 1 change. Yeah, 2 plus I is not a root of, we're down the wrong function. Sorry, guys. Good catch. Thanks, Chris. Go through the entire volume. I'm like, I should have multiplied it out. I'm glad you did. All right, so. I should end up with all real coefficients when I'm done. Because there shouldn't be any more complex numbers here after I do the second set. This adds together and makes 1. That's not working right. Why do I still have a negative root? What the hell did I do here? Did you get all those values? Anybody else?
Yeah, it all looks correct.
Okay. Another one. Add those up. You get 1, and then I multiply that by 2 minus I. This is not working. Why? It's not the negative 50, that's at the end. That shouldn't have derailed the beginning. Minus x cubed minus 17x squared plus 55x minus 50. 1, negative 1, negative 17, 55, negative 50. Those are all correct. Bring down the 1, multiply, add up. That's a 3. That's the problem. That makes this 6 minus 3i. There we go. Add those up, I get negative 10. Negative 10 times 2 is negative 20. Negative 10 times negative I. Why do I have negative 2i there? I should say negative 10i. Negative I times negative 10 is plus 10i. That adds up to 0. That's a fail. All right, so I've got if x equals 2 plus I, then x minus 2 minus I is a factor. And here, if x equals 2 minus I, then x minus 2 plus I is a factor. So I can write this as that factors into 5 and -2. So my roots here were x equals 2 plus I, x equals 2 minus I, x equals 2, and x equals -5. I'm going to use the same problem to illustrate the intermediate value theorem and the bounded theorem. Okay. So let's just put the same problem up. My a sub 0 is -50, which means possible factors are, oh, there's a lot here. Plus or minus 1, plus or minus 2, plus or minus 5, plus or minus 10, plus or minus 25, and plus or minus 50. My a sub n equals 1, so it's plus or minus 1, which means this is my p over q. When the leading coefficient is 1, it's just the factors of the last number. So watch what happens when I use check 2. Let's do 2 using synthetic division. This didn't work. What the fuck? Oh. All right, let's not check 2. Let's check the other one. Let's check -5. The 2 plus I is throwing it off. Let's try -5. I picked a shitty problem to try this on.
Wait, how does 2 not work?
It's going to work is the answer. It doesn't work for showing the intermediate value theorem
Oh, okay.
or the bounded theorem. Well, I was going to try to show the bounded theorem. So hopefully this works here. Wait, that's not -30. That's -65, which is -10. And that's 50, which is 0. All right, the bounded theorem said if C is less than 0, C here is my -5. And the signs alternate. There is no root lower than -5. which means I could immediately cross out -10, -25, -50. Those are all gone. They're not possible roots anymore. Let's go back and take a look at a problem we had before. And look at the intermediate value theorem there and the bounded value theorem there. Let's take a look at f of x equals 6x cubed minus 37x squared plus 32x plus 15. This is the one where I gave you x equals 5 was the root. You don't usually have that information given to you though. So let's see what we could have done when we started with this. So by Descartes' rule, I see that it changes signs twice. 2 sign changes, which means 2 positive roots. I should get 1 when I do f of negative x because they need to add up to 3. But let's just check it real quick and make sure I know what the hell I'm talking about. We've only got 1 sign change here, so 1 negative root. Okay, let's do our P's and Q's here. A sub 0 is 15, which means I can have plus or minus 1, plus or minus 3, plus or minus 5, plus or minus 15. A sub n is 6, which means plus or minus 1, plus or minus 2, plus or minus 3, or plus or minus 6. So if I look at all my possible roots, writing them out, my P over Q, I can have them all over 1. I can have them all over 2. I can have them all over 3, plus or minus 1/3. 3 over 3 already shows up as plus or minus 1. I'm not going to worry about that. 5 over 3 we don't have yet. And 15 over 3 is 5, and we already have that one. So I don't need that one. And now I do my 6s. I can do 1 over 6. I can do 3 over 6, which is 1/2. And I already have my 1/2. I can do 5 over 6, which I don't have yet. And I could do 15 over 6, which reduces to 5/2. These are all my possible roots. This is fucking holy shit. I'm going to write them in order. Let's start with the positive roots or the negative roots. It might help to go look at some of these and go, what are these values here? I've got 0.5, 1.5, 2.5, 7.5 there. 1/3 is 0.33. 5/3 is 1.667. 1/6 is 0.16. And 5/6 is 0.83. So if I'm arranging them as negative numbers, I'll start with my big dog, my -15. Then I've got a -7.5 is next, which is my 15/2. Then I've got the 5. Then I've got the 3. Then I've got 2.5 is next, which is 5/2. I've got 1.67, which is -5/3. I've got 1.5, which is -3/2. Just underline it as I do them. Now my next one is -1. This is a pain in the ass, right? Then my next smallest is -0.83, which is the 5/6. I got -1/2 and -1/3 and -1/6. I can reduce this order and make them all positive. This is some daunting shit, right? What happens if I plug in f of 1 and f of -1? Those are the easy ones to try right away. F of 1 is 6 minus 37 plus 32 plus 15. Let's see, that's -5, 10, 16. If I do f of -1, I've got -6 minus 37 minus 32 plus 15. This is negative something. I have a sign change between these two. The intermediate value theorem tells me there is a root between them. There is a root somewhere between here and here.
I thought the intermediate value theorem was if you did f of a and f of b.
And they change signs. This is f of a. The a and b are placeholders.
Oh, okay.
You would never stick in a and b, and there's no way to compare them if they change signs. That's why I'm glad I did this, because that clears up the. You don't plug in a or b for intermediate value theorem. You plug in possible answers. And if you see a sign change, what is this one right here? This is -69, -75, -60. These are different signs. As long as they're different signs, there is a root between them. So, can I narrow it down more? I don't even have to check possible roots. What if I check f of 0? F of 0 gives me right away 15.
Positive 32.
Plugging in positive one? If I stick in f of 0, I get 15, which means there's actually a root between 0 and -1. That narrows it down to this. So I try one of these until I find it. If I find, like, if I try, let's try -1/2. I know -1/2 doesn't work because I know what the answer is, but let's try -1/2.
Also, what's it called? There's only one negative root, so
There's only one
Make
negative
them-
root, so if we find it, we cross off all the negative roots. That's a good point. We can do it right now. I know there is a negative root between, or there is a root between -1 and 0, which means all those are gone. Because it's our only negative root by Descartes' theorem. My negative root has got to be one of these four. So I've crossed all of these, and all I've done is 1, -1, and 0 so far. These weren't like calculator problems so far. Now, this is where it gets a little hazy. So let's try -1/2. I know -1/2 doesn't work, but I want to illustrate the idea of how you use this theorem. We have 6, -37, 32, 15. This is probably easier if you plug it into the calculator, but I'm not sure. I'm just going to walk through it and find out. Not so far. Did I do this right? That's a -11. Okay. That's where I did it wrong. All right. So I had f of -1 is -60. I have f of -1/2 is -11, my root here. And f of 0 is 15. I just showed my -1/2 is not one of them. And there is a root between -1/2 and 0, which is these two. These two are between -1/2 and 0, which means the -5/6 is already out also. I'm down to 2 possible roots. X equals -1/3 is one of them. We did that before. That's how the intermediate value theorem works. Does that make sense? So you plug in numbers, and if they have opposite signs, the answer, the remainder, the last digit here, whatever that is, if they have opposite signs, there's a 0 between them, which means you can start, if you have these sorted in order, that's why I put them in order. It was a pain in the ass to put them in order, I know. But by doing that, I showed right away by doing f of -1. I didn't show that. I could have done, if I had done f of -1 doing synthetic division rather than this. By the bounded theorem, my C or my K I wish they didn't switch between them. K here was -1. And my signs alternate from sky. I like to call it sky division because shit just falls down. Signs alternate from synthetic division. Which means there's no root less than -1. Which means I could have crossed off all of these before we even did what Christopher pointed out. By doing -1, I could have crossed these off all right away. If I'd done synthetic division rather than putting it into this thing. Does that make sense? The bounded, if you work with these theorems, they will help. See, let's do one more idea in this section. My shit is all over the place. This in a second to figure out where this go. Let's do one more idea. Let's see what I want to do. Let's say we know the zeros. We have zeros of x equals -3, -2, and 5. And we know f of -1 equals 6. Find the original equation. Original function. So if I rewrite these become x plus 3, x plus 2, and x minus 5. Let's try sticking in f of -1 real quick and see what we get. -1 plus 3. -1 plus 2. And -1 minus 6 or minus 5. It gives me 2 times 1 times -6, which is -12. That does not equal 6, right? Which means there must be something in front of it. There must be some multiplier. So if I redo f of -1 with that in there, I have a times 2 times 1 times -6. I need that to equal +6. Not 6. So I've got -12a equals 6. So a equals -1/2. And I can write my initial function as f of x equals -1/2 times x plus 3 times x plus 2 times x minus 5. And we can multiply it all out. We probably should. X plus 3 times x plus 2 is x squared plus 5x plus 6. The next one I can't do as fast, so I'm going to have to multiply them all out. I got x cubed minus 5x squared plus 5x squared minus 25x plus 6x minus 30. So I've got negative 1/2 x cubed. The x squareds go away, right? Negative 19x minus 30. So that's got to be the original function. Ready for some more? These are just quick to reinforce the intermediate value theorem and the bounded theorem. So let's say we have f of x equals let's show that there is a 0 between 1 and 2. If we do f of 1, I get 2. And I get negative 3 for f of 2. These are opposite signs. And so there is a 0 between them. What the intermediate value theorem does not guarantee, it does not guarantee that it is a rational 0. Okay. But you can at least narrow it down and check those. You may, oftentimes you get it's one of them, but sometimes it's not, and it's just okay. That was just it's an irrational number in there. There's no, it doesn't help you. Showing the bounded theorem on a couple things. F of x equals x to the 4th plus 5x cubed. Nope. 5x squared plus 3x minus 7. Let's show there is no 0 greater than 1. We do that by doing sky division or synthetic division. I keep doing it. These are all positive. And C equals 1, C is greater than 0. If C is greater than 0 and the outcome is all positive, there's no root that's bigger than that. We can also show there is no 0 less than -2. So when you do synthetic division, you get those results. C is less than 0, and these alternate signs. That's the other scenario of that bounded theorem. It's a lot to remember. There are a lot of different little things here to help. And chances are you won't remember a lot of these for a while. They just you could try to like make flashcards to force your memory on them, but thinking of it while you're using them, it just takes a lot of practice. And in all reality, in the real world, you would graph this shit and you'd find the zeros that way on a graphing computer, right? The idea here, and I'm aware of that, the idea here is to get you familiar and practice doing these different types of techniques, because it's like a skill set that will help you in calculus and stuff beyond. So I realized there is a better way of doing this. Okay. But getting practice with this will help you in the long run. It builds your mathematical skills. All right, it's 5 o'clock. Get the hell out. All right.
I have a question.
Yeah.
So you mentioned that if we take the summer school trigonometry, that we can have next semester after that, we could have you for calculus?
Yep, I'm teaching calculus 1 in fall.
Well, I plan on doing that.
All right, yeah, it's I think it's called Pre-Calc B. I think they've renamed it.
Seems pre-calc and trig, pre-calc B.
Pre-Calc A is college algebra, Pre-Calc B is trig. It used to be called college algebra and trigonometry. I don't know why the hell we renamed it, but we did. I don't know if these are the right. There's a lot of notes today. This is madness. Madness, I tell you. Oh, plus also, like I showed these are like the intermediate value rules. These will be, I'll scan them separately to put them in a document for you guys, but it's like the shortcut rules all in like put together so you can see what they are. There's a lot of rules, but they help find the solutions.
Remember the last one we did where they all turned out? How does that like
The book will, if you want to see a proof of it, the book will walk you. If you go into like,
just like a rule that
it's a rule, but they actually have a proof for it. Like if you want to see the proof, you go into the video or library multimedia resources in the My Math Lab, And just look at the chapter on 3.4. Intermediate value and bounded are in 3.4. Ah.